The next type of FRQ that we'll be dealing with are data tables. They'll give you a table. You need to be careful that you don't assume what's happening between the points given. Some might assume, oh, it's increasing from 0 to 55. You don't know that. It may go down to negative, back up to 55. So be careful about your assumptions. Let's read this. The velocity of a particle p moving along the x-axis is given by the differential function v of p. Units meters per hour. So those are all given here, so I'm not going to pull that out. All right, so let's just do this. First one. Justify why there must be at least one time t from point 3 to 2.8, which the derivative of the velocity, which is the acceleration, equals 0 meters per hour. So comment on data table problems will be intermediate value theorem and mean value theorem. Okay, so intermediate value theorem is you want to prove that your function, in this case would be v of p, equals a particular number. Like obviously, if it goes from 0 to 55, it must contain every number between that. So we could see that, oh, it has to equal 20 at some point because it goes from 0 to 55. Now, one condition for the intermediate value theorem to work, it must be continuous. But the fact that it's differentiable means it is continuous. Okay? The other type is you have your function and you want to prove its derivative must equal something, and that's what we have. We want to prove that the derivative of v must equal 0. So between 0.3 and 2.8. This is the mean value theorem problem, part A. So for mean value theorem to work, you must have a differentiable function on the open interval and a closed function, continuous function on the closed interval. Well, here is where this information is important. You know that v of p is differentiable. So you have differentiability. You need to state that. Okay, it's part of what needs to be stated in order to use the mean value theorem. So v of p is differentiable. And I'm going to say, therefore, v of p is continuous. Okay, so important to know, if something's differentiable, it must be continuous. That's a theorem that we had. Now to think about this, when is a function not differentiable? Remember, discontinuities and sharp points. So therefore, if it is differentiable, it must be continuous and there must not be sharp points. Okay? So those are two conditions that must be true for for mean value theorem to work. And what mean value theorem says, there must be at least one point right here. There must be at least one time t in this interval such that the average rate of change equals the derivative. So that's what we're going to do. If you look, the average rate of change between these 2 points, f of b minus f of a over b minus a, is going to be 0 because your y values are the same, so your y value is not changing. Okay? So the conclusion, we'll do this. F at 2.8 minus f at 0.3 over 2.8 minus 0.3 equals 55 minus 55 over 2.8 minus 0.3. I didn't give myself enough room, which equals 0. So we have found the average rate of change is 0. Therefore, now we can conclude there must be at least one time. Basically, we're going to copy this. Okay, we're going to copy that. So we have shown that the average rate of change is 0. And so my conclusion, therefore, and remember, I'm just going to copy this, there must be at least one time t, because that's what I'm trying to find. least one time t for, what, t being between 0.3 and 2.8, where v prime of p, excuse me, I'm messing up here, v prime of p equals, wow, this thing's tripping out on me, equals 0. Okay, and just to remind you, if you don't remember the mean value theorem, if we have a continuous function and we find the average rate of change, so the slope between these 2 points, that's f of b minus f of a over b minus a. There's got to be a point where the derivative, which is the slope of the tangent line, equals the slope of the secant line. So the average rate of change equals instantaneous rate of change. And that occurs if it's continuous and differentiable, no sharp points. So that's what we have shown, differentiable and continuous. We found the average rate of change is 0. We found this is 0. Therefore, there must be a place where the derivative, which is the slope of the tangent line, is 0. Therefore, there must be at least one time t where the derivative of v is 0. Okay, so that's part A. Part B, we're going to approximate. I'll do it over here. And we are doing the trapezoidal rule. 3 subintervals, so we're going 0 to 2.8. So we're going from here to here, 3. 1, 2, 3 subintervals. Okay, here is what I require you to show me. So trapezoidal rule, you have to take the area of the trapezoid, which is 1/2, the sum of the bases, which is going to be VP at 0 plus VP at 0.3, and then the width between them is going to be 0.3. This is very similar to area of a triangle, except a trapezoid, you have to add the 2 legs. Plus 1/2, and then it's going to be the V's at these points, 0.3 and 1.7. So it's going to be VP at 0.3 plus VP at 1.7 times the width, and the width between these two is 1.4. And I have one more, and I am running out of room. Let me squeeze this in here. So the last 2 are going to be between these. So I'm going to do VP at 1.7 plus VP at 2.8. Wow, I'm just out of room here. I'm messed up. Here, let me put it lower because that's getting ugly. You gotta be able to follow this. 1/2 VP at 1.7 plus VP at 2.8. And the width between these two is going to be 1.1. So times 1.1. That is my answer, right? I don't have to do anything else. I am done. I've completed this. Don't simplify that unless you have to. There are certain cases where you might have to do that, but not in this case. All right, so we answered B. Now we should read the question, make sure we answered it correctly. Use the trapezoidal sum to approximate the value. Yeah, so we have done that. You don't have to simplify that at all. All right, let's keep going. Oh, actually, I'm a liar, pants on fire. We got to find these values. We got to plug those in. So let me do that real quick. VP of 0 is 0. VP at 0.3 is 55 times 0.3. That's going to be 55 plus negative 29 times 1.4. And that's going to be negative 29 plus 55 times 1.1. There's my answer. So you need to show where these numbers come from. I know sometimes the scoring guidelines, they go right to this line. I require you to tell me where those numbers came from. Numbers shouldn't magically appear out of nowhere. You need to tell me where they came from. So I require this line and then plugging in the numbers. Okay? Let's go to part C. A second particle Q also moves along the x-axis. And this time we have a function for Q. So it's an actual function. And this is a calculator question, by the way, just to let you know. Find the time interval during which the velocity of particle Q is at least 60 meters per hour. Find the distance traveled by particle Q during the interval when the velocity of the particle Q is at least 60 meters per hour. I said miles, meters per hour. Okay, so we have to use our calculator. And first of all, we need to find out when the velocity equals 60. Because when it equals 60, it's going to be around that where it's going to be over 60. So part C, I want to know when VQ of t equals 60. And that's all calculator work. So let me get a calculator out. And we will plug this in. All right, so y equals, and I can't see my formula, so let me go ahead and bring up the test on my computer so I can see the formula. There we go. So it's 45, and then we have square root of t, but we always use x. And then we have cosine of 0.063 x squared. All right, so that's my function. And I want to know when that equals 60. So I want to graph 60. And then let me go ahead and pick my windows. So my window, if you look at the problem, I believe they tell you the time interval. It's going to be 0 to 4. They tell you that. So I want to start at 0 and end at 4. Now I know it's going to go at least up to 60. I'm going to go up to 100 because I want to know when it equals 60. Let's graph this. And now you can see what's going on. So the blue line, this blue line is my function. This red line is 60. We can see it's greater than 60 between these, but first we have to find where they're equal. We have to find these 2 points. So I'm going to do my calc intersect, and I'm going to get that, and it's 1.866. I'm going to store that. My home screen, X, store, A. So let me go back, 1.86618. And let's find the other intersection point. Let's get this one. Okay, 3.519. Let me store that. Go home. So I'm going to take X, store that as B. 3.51917. 3.51917. Hopefully I remember that right. And so those are the 2 points where it equals 60. And from this, we know it's greater than 60 between that. If you look at the graph, it's going to be between those two numbers where it's greater than 60. So I'm going to state that. So VQ of t is greater than 60. And I'm going to tell you for what region. For t between A and B. All right, so that's that part. Let me continue reading. Find the distance traveled by particle q during the interval when the velocity q is at least 60 meters per hour. So going back to the graph, they want the total distance traveled from A to B in the period where it's traveling faster than 60. Okay? And so this is where you have to know your formulas. If you integrate velocity, it gives you displacement. But if you integrate the absolute value of velocity, it gives you total distance traveled. I'm going to go from A to B. And we're just going to do that in the calculator. And in this case, we actually don't need the absolute value because the velocity is always positive. It's only when the velocity gets negative do you need the absolute value. But let me go ahead and do this in the calculator. So math 9, I want to go from A to B, and I want absolute value. So that's under the math menu, numbers, absolute value of, and I want my y1. Hit that 106.108 or 109. Approximate. You could do 108 or 109. Either way is fine because we are either truncating or rounding off. So now that we found that, we should state it. So the total distance traveled by particle q during the time interval from A to B is 106.108 meters. And that's part C. We have one more part D. At time t equals 0, the particle q is at negative 90. Using the results from part B and the function v of q in part C, approximate the distance between the particles p and q at t equals 2.8. Okay, so let's see what our answer was from part B. Okay, so when we get this integral, that gives you the displacement. That gives you the change in position of the object. Okay, so if we know the starting position and how much it changed, we know its final position. Okay, now more important information, the particle P starts at the origin at time t equals 0. So the starting position is 0. The answer to B is its final position because the integral of the velocity gives you change in position. Okay, this is all stuff that we should know. So we can get the position of particle P. Let me do that. I'll call it x of P, the position of P at the end of 4 seconds equals the starting position, which was 0, plus the change in position, which is the integral of Vp of t from 0 to 4. Okay, actually it's 2.8, not 4. Okay, this should be part of your everyday thinking. final position, starting position, change in position. We did this actually with accumulation. The starting amount plus the change to get the final. So velocity is the change in position over change in time. It's the rate of the position. So when you do velocity, that's the rate of the position, you integrate it, it gives you change in position. So if I know my starting position plus change in position, it gives me my final position. And this is actually the answer from part B. Now this, I don't want to write all that down. That's a lot of writing, and I don't want to simplify that. So I'm gonna give it this. Let, what should we call that? I'll give it M. So now we define that. So this would be 0 plus M, or M is the final position of that particle. Now we have to do this. We know the starting position of particle Q. We need to find the final position of particle Q. Okay? So I need XQ at 2.8. Well, it's going to be the starting position of Q plus the change in position, which is the integral of the velocity of Q. Now I want to go from 0 to 2.8, and that we just pop in our calculator. All right. Our starting position of Q, they tell us, is negative 90. So it starts at negative 90 plus this integral. So pop that in your calculator, and what you're going to get is 45.937653. So that's the final position of Q. That's the final position of P. So if you want to find their distance, you subtract those. Now, we never actually, now that I think about this, this was a calculator question. It wouldn't have been so bad to simplify the part on top, make our life easier right now. That comes to 40.75 if you throw this in your calculator. So let's choose 40.75. So the distance between them would be that minus that. So that will be our final answer. Therefore, at t equal 2.8, the distance between the particles is 45.937653 minus 40.75, and those units will be meters. Okay, you don't have to subtract those. That's my final answer. This is 2018 FRQs, question number 4. Another data table analysis. The height of a tree at time t is given by the twice differentiable function. So they're telling it's twice differentiable. That means h prime and h double prime both exist. H of t is measured in meters, which they give us here, so it's fine. And t is in years, we have that there, so that's fine. Now, the only thing you might want to add, this is the height of the tree. Okay? So we've got all of our information. Part A. Use the data table. Let me erase this part above here. We'll do part A above. Use the data table to estimate h prime of 6. So we want the instantaneous rate of change of h at 6, or the derivative of h at 6. We don't have the function h, so we can't just take the derivative. That's why we're going to estimate it. And this is a very common question on data table problems. How do you estimate that? I'm going to give you a rough review of how we do that. If we were to plot these points, and I'm going to do them real roughly, 1.5, 2, 3, actually 2, 1.5, 3, 2, 5, 6, 11, 7, and 10, 15. So actually, let me change it around because it's just, these are approximate. So let me do this slightly differently. Let's suppose it looked like this. If I plot the points, then we have some kind of a curve like that, right? And we want the slope of the tangent line at 6, where 6 is somewhere around here. So we want that slope of that. Now, what's the most logical thing to do to estimate the slope of that? You would take the 2 points around it and find the slope between those two. So you find the average rate of change of 2 points around it, and that approximates the slope of that. Very common. Now, it wouldn't make sense to use these two. It wouldn't make sense to use these two. You'd want to use the 2 points that are directly next to the point we're trying to approximate. So for part A, you would do h prime of 6 is squiggly equals, because it's not exact, and we want to do h of 7 minus h of 5 over 7 minus 5, which is 11 minus 6 over 2, 5 over 2. So our answer is going to be 5 over 2, but let's keep reading the question. This is where it gets important. Using correct units, interpret the meaning in the context of the problem. Okay, let's get our units right here. The units for h, meters. And the units for this is time in years, so it's going to be meters per year. So those are our units. But what does this mean? So the derivative is 5/2 meters per year. What does the derivative tell you about a function? If it's positive, h is increasing. So we know h is increasing, but what is h? H is the height of the tree. All right? So the height of a tree is increasing. I'll put that down. The height of the tree is increasing at the rate of 5/2 meters per year when t is 6 years. Okay? So it's as simple as that. You have a derivative, it's positive, you know h is increasing, h is the height of the tree is increasing. This is a rate, so at the rate of 5/2 meters per year when t is 6. Okay? So that's going to be part A. Part B. So this is very similar to the last one we did. You're given a data table. Intermediate value theorem and mean value theorem are very common. We want to show the derivative of derivative of h, and this is h. So that screams mean value theorem. Okay? I messed up, sorry. They want to show you what h prime, that the derivative of h must equal to. So to show that the derivative of this function equals something on a data table, that's going to be mean value theorem. So part B, in order for mean value theorem to work, I need differentiability and continuity. But we're given differentiability, so I can just state that. H is differentiable. Okay? And therefore, H is continuous. So you need this statement. Because H is differentiable, therefore H is continuous. So that's going to be 1 point, something that I require you to write down. And it's a conclusion because H is differentiable, therefore H is continuous. You can't switch that around. They give you differentiability. Use your theorem to get continuity. Okay, so we have from 2 to 10. From 2 to 10, we need the average rate of change to be 2. Now we got to find 2 points in this region that will give us an average rate of change of 2. All right, and it's kind of trial and error. Like if you look at these two, that's going to be 2 minus 1.5 is going to be a half. That doesn't equal 2. Let's look at these two. 6 minus 2 is 4. 4 divided by 2, there it is. So you just got to kind of search and try to find the 2. Next, what we're going to do is h of 5 minus h of 3 over 5 minus 3. So that's the average rate of change, also known as the slope of the secant line. And that's going to be 6 minus 2 over 5 minus 3, which is 4 over 2, which is 2. And the units, h is measured in meters, t is measured in years, so it's going to be meters per year. Okay, so you've shown the average rate of change is 2. The conclusion is, therefore, the derivative must equal 2 in that region. So your conclusion is going to be this. Therefore, there must be at least 1 times t, blah, blah, blah. You're just going to copy that because you've shown all the things necessary for that to be true. So therefore, there must be at least 1 time, t for t between 2 and 10 such that h prime of t equals 2. Dunno. Now you might say, hey, you used 3 and 5. How come now you're saying 2 and 10? Because 3 to 5 is inside of 2 and 10. So I still have it inside of 2 and 10. Okay, that's part B. Now we're going to part C. Oh, trapezoidal again. 2 years in a row they use trapezoidal. The average height of the tree. So part C, key word here, average height of the tree. In chapter 5, you learned how to find the average of any function. The average height, you would integrate your height from 2 to 10, and then you divide by the width, 10 minus 2. By definition, that's how you find the average of any function. Okay, here you got to be careful not to lose track of 10 minus 2. It's easy to do that. So we're going to do trapezoidal again. I require you to show where everything comes from. So we're going to have 1/2. And is it from 2 to 10? Is it really that far? 4 subintervals. Wow, that's a lot of subintervals. So 1/2, the sum of the bases, which is h of 2 plus h of 3. And the width between those is 1. 1/2, the sum of the bases, which would be h of 3 plus h of 5, and the width between those is 2, plus 1/2 h of 5 plus h of 7, and the width between those is 2. Man, I'm going to run out of room again. 1/2 h of 7 and h of 10. h of 7, h of 10, and the width of that is 3. Hopefully y'all follow that. Sad. I'm out of room. Okay. Now plug in the actual numbers. So I need h of 2 I got 1.5 and 2. And then I have 2 and 6 and a width of 2. And then I have 6 and 11 and the width of 2. And then I have 11 and 13 and the width of 3, all over 8. So that is our answer. Use the trapezoidal for subintervals, the average height. I can call that something. We can say let M, I don't know why I chose M equal that. Then I can conclude the average height of the tree over the time interval two to 10 is M, and it asked for units. It did not ask for units, but I'll put meters. Bam. So that's my answer to part C. For part D, I'm going to show you 2 different ways to approach this, but let's break down the question first. So the height of the tree is G. G is the height. Important to know that. And X is the diameter of the tree. And you can note the meters if you want. They're both in meters. Now let's take this statement. When the tree is 50 meters tall, the diameter of the tree is increasing at the rate of 0.03 meters per year. So that statement, the diameter is X, the rate of change of X expected time, when the height of the tree is 50, when G is 50, is 0.03 meters per year. So that's a rate of X. Now read the second part. According to this model, what is the rate of change of the height of the tree with respect to time? They want to know how fast G is changing as time changes at the same 50-meter tall tree. And that's what they're looking for. So if you look at this, basically it's a related rates problem. You have 2 rates, the rate of growth of the diameter and the rate of growth of the height, and you have a function here where those 2 are related. So let's go ahead and write that down. This is part D, obviously. So we need to take the derivative of both sides with respect to time. Now, G is a function of time because as time goes on, the height changes. And X is also a function of time because as time goes on, the diameter of the tree grows. So both of those could be considered functions. So I'm going to treat those as box, okay, as functions, and boxes in chain rule. What's the derivative of the left side with respect to time? That's the change in G over change in time. On the left side, to take the derivative, it is a quotient rule. So it's going to be low d high. Now watch out. The derivative of 100x is going to be 100. That's a constant. You copy that. Times the derivative of x. But x is a function. It's box. So the derivative of x will be dx dt minus high, copy the top, d low, the derivative of 1 is 0, and the derivative of x is dx dt, all over low squared. Now it's a matter of just plugging everything in. Okay, we have one issue. What is x? Well, when g is 50, can we solve for x? I think we can. I'll just do some side work. When g is 50, we have 50 equals 100x, 1 plus x. I'll multiply both sides by 1 plus x. Subtract 50x from both sides. And we get x equals 1. So we know x equals 1. So we replace all the x's with 1. dx dt with 0.03. Replace the x with 1. dx dt with 0.03. I think my parentheses are good there. 1 plus 1 squared. That should be the answer. Let me go ahead and simplify that on the calculator. I know, is this a calculator problem? Let me see. What number is this? No, it's not a calculator problem. So I would leave my answer like that. Now, rereading the question, according to this model, was the rate of the change of the height of the tree with respect to time in meters per year at the time when the tree is 50 meters tall. So that should be sufficient. I just want to make sure these numbers come out right. So let me do this real quick. And my parentheses are actually off a bit here. So let me fix them. That's better. Okay. You can fast forward through this if you don't want to wait for me to do this. I just want to make sure I'm getting the right answer. Let's see, minus 3 divided by 4. Yes, so I got the right answer. It's 0.75. There is another way. Well, it's actually the same way, but another way of looking at it. So let me go ahead and do that for you. You can look at it in terms of chain rule. Okay? So let me erase all this. So in chain rule, we want dg dt, right? We have dx dt. I'm going to put this over here. Now you see, that gets us our dt on the bottom. We want a dg on top, and we need dx's to cancel, so we need a dg dx here. So a dg dx would get these to cancel, end up with dg over dt, and that's what we want. So this would be a chain rule view. Well, how do you do that? What's dg dx? That's just going to be the derivative of this with respect to x. So that would just be a low d high, low d high minus high d low all over low squared times dx dt, which we already calculated. I'll just leave it dx dt. And then you just plug in 1 again for x like we found before. And this is 0.03. And what do we get on top? This is 200 minus 100. So it's going to be 100 times 0.03 over 4, which is 3 over 4. And that's the same answer as last time. So that way is another way you can do these. So there's a related rate that could be done using, my brain just went blank, using chain rule. All related rate problems can't be solved using chain rule, so be careful. But chain rule is always an option to try first. All right, that's it for this video.